My name is Mateo Sayers, and today I'm going to be going over my responses to the final exam free response. I am in section 2 of BA 642, Statistical Analysis. Here we have my table of contents. We're going to start with Chapter 12, Case Problem 1, A Bipartisan Agenda for Change, and we're going to go from there. Okay, so for the Case Problem 1 for Chapter 12, this case involved a follow-up survey regarding whether or not the New York State government works and was conducted with 100 people in the western region of New York. They were asked three questions, and their political affiliation, yes or no, was recorded for each question. Here we have a table showing the total of each response per political affiliation. There was a total of 200 yes answers and a total of 100 no answers. So around two-thirds of the people, or 33 point or 66.66% said yes to the questions. So let's start with our our null hypothesis, and that is the response to question one is independent of party affiliation. The alternative hypothesis for this test is going to be the response to question one is not independent of party affiliation, and we're going to use a significance level of 95%. From the data given, the following pivot table and expected frequency tables were constructed in Excel. And this is the formula I used to make the expected frequency table. The original table right here, like the observation table, was created using the pivot table option in Excel. The p-value was then calculated from this expected frequencies table using the chi-square test function in Excel, in which I compared the observation values with the expected frequency values. This gave us a p-value of 0.006, which is smaller than the alpha of 0.05. Thus, the answer to question one is not independent of party affiliation because when the p-value is less than the alpha value, then we reject the null hypothesis. So the same steps as part two were taken in regards to the table and how I generated them. I just used the pivot table insert in Excel, and then I used the sample formula for all cells in the expected frequency table. Then the second question, we reviewed the the second question asked to the people in New York, and that should there be more restrictions on lobbyists, whereas in the first question we asked, should legislative pay be cut for every day the state budget is late? Again, the p-value was calculated from the expected frequencies table using the chi-square test, and the p-value ended up being 0.156, which is greater than the alpha value of 0.05, which we got from our significance level of 95%. So this means the null hypothesis cannot be rejected this time around. So the answer to question two is independent of party affiliation. Finally, we did the hypothesis test for question three to determine whether or not it was independent of party affiliation. And the question was, should there be term limits requiring that legislators serve a fixed number of years? Again, the observed table and expected frequency tables were used, and the p-value that was calculated from the expected frequency table was 0.078, which is greater than the alpha of 0.05, which means null hypothesis cannot be rejected. So we must accept it, and the answer to question three is independent of party affiliation. And yes, it does appear that there is a broad support for change across all political lines. This conclusion was made due to the ratios of yes for each party affiliation to all the three questions. The Democrats answered 56% yes, independent answered 61% yes, and Republicans answered 78% yes. Since all three of these questions had to do with change to the government in New York, or change to the government in general, these answers indicate that there is a broad support for change, although slightly less for Democrats, but overall, the majority is yes for change. Moving on to chapter 12, case problem two, the Fuentes Salty Snacks Incorporated case problem. So they wanted to determine whether or not they have successfully penetrated the US market because they made a new flavor of potato chips. They have 40, they called 40 stores in the 8 US sales regions they possess, and they asked the store if they currently carry their new potato chip. Below is a table of how many stores said what in each of the 8 sales regions. So New England, 27 said yes, 13 said no, Mid-Atlantic, 29 said yes, 11 said no, and so on. The total amount of stores was 220, that said yes was 224, and that said no was 96. That's out of a total of 320 stores. So 70% carried Fuentes' new potato chips in store and 30% did not. We did a hypothesis test once again, similar to the previous case study, where we wanted to test to see if the proportion of grocery stores that carried the new Fuentes bacon potato chips is equal in all 8 of its US sales regions. And the alternative hypothesis was that they were not equal across the 8 US sales regions. Again, we used a significance level of 95%, and that's our alpha value. So from the data given, the following pivot table and expected frequency tables were constructed once more in Excel using the pivot table function. We'll insert and then the sample calculation for how the expected frequency table is highlighted right here. And that's for the highlighted box right here. And then it was just dragged over and dragged down. And then from there, the p-value was calculated from the expected frequencies table. For using the chi-square test, the p-value was 0.0014, which is less than the alpha value of 0.05. So the null hypothesis is actually rejected here, and this means that the proportion of grocery stores that currently carries Fuentes' bacon potato chips is not equal. So they actually differ across the 8 different regions. So yes, the results of the hypothesis test in part 2 provide evidence that the level of penetration. So yes, the results of the hypothesis test in part 2 provide evidence that the level of penetration for Fuentes' candied bacon potato chips differs across its 8 US sales regions. So the expected penetration level was 28 for like all 8 of the sales regions. The sales regions that were higher than this were the Mid-Atlantic, Great Plains, South Atlantic, and Deep South. And sales regions with lower penetrations than expected were New England, Mountain, and Pacific. And the Midwest actually had dead on of 28, so that couldn't be included in either of the categories. All right, moving on to chapter 14, case problem 2, U.S. Department of Transportation. In this case problem, it was asked to determine whether or not there was a relationship between the two variables of percent of drivers who have licenses that are under 21 and fatal accidents per 1,000 licenses. This data was collected in 42 cities. And here I create a scatter plot, and Excel filled in the regression line and the R-squared value. So the R-squared value is 0.7046, which means that 70% of the dependent variable, which is fatal accidents per 1,000 licenses, 70% of that can be predicted from the independent variable, which is percentage of licensed drivers under 21. The regression line was generated by Excel, and then the Excel minor analysis tool pack in Excel was used to perform linear regression. Just to double check the auto-generated linear regression line. And from there, the B naught or intercept value was negative 1.5974, and the slope value was 0.2871. So that's the linear regression line equation, which is actually exact to the one Excel provided. So for every percent increase of licensed drivers who are under 21, there is an increase of 0.2871 fatal accidents per 1,000 licenses. And since the R value is 0.8394, we can see that there's a positive correlation between the two variables, and a positive relationship, and the R-squared value of 0.7046 indicates a strong correlation between the two variables. So I can conclude that there is indeed a positive linear relationship between these two variables, and that the number of licensed drivers under the age of 21 can actually be used to predict the number of fatal accidents per 1,000 licenses, and as seen by the R squared value, about 70% of that can be accurately predicted. All right, and moving on to Chapter 15, Case Problem 1, Consumer Research Incorporated. Consumer Research Incorporated was hired to investigate and predict how much credit card users charge to their card annually. Data was collected on income, household size, and amount charged for 50 consumers in order to find the best predictor for how much they're going to charge in a year. So the dependent variable that was gathered here was the amount charged, and the two independent variables were annual income and household size. And some descriptive statistics here, just averages and standard deviations. And it's important to note that household size, that involves number of people, so you can't actually have a fraction. So those were corrected down here to round it down to 3, and the standard deviation must be rounded up to 2, because you can't have 0.4 or 0.7 of a person. So the average amount charged to the credit card was around $3,964, a standard deviation of 933. So initially, we're going to use the annual income as the independent variable to see how it relates to the dependent variable of amount charged at the credit card annually. So the linear regression was produced in Excel, similar to the previous case. And from this linear regression output, the estimated regression equation can be determined from the intercept coefficient and the annual income coefficient here, which is the intercept and slope. So the regression equation comes out to be 40.48x plus 22.04. So the multiple R value is 0.631. This can be seen right here. And the R squared value is 0.398, as can be seen right here, indicating that the relationship is positive, but the correlation is not very strong. We know it's positive since the R value is 0.631, but the R squared value of 0.398 isn't too strong of a correlation, so that's not the best predictor. However, moving on, when using the household size as the independent variable, the following linear regression data was generated in Excel. And from this one, the regression equation is this. And this time the multiple R value was 0.753, which indicates a positive relationship. And the R squared value was 0.567, which still isn't the highest value an R squared could be, and it's not the best it could be, but it is higher than the previous independent variable used, which was annual income. So like the number of people in the household is actually a better predictor for the amount charged to a credit card annually. And when both of these independent variables were used together, this is the linear regression data that was produced. And as you can see here, the R squared value was much higher when these independent variables were used together to predict the dependent variable, and the R value was 0.9, which shows, again, positive correlation. This is the new linear regression equation using the two independent variables. As you can see, we have an X. This is the new regression equation with the two independent variables. As you can see here, there's an x1 and an x2. And from here, we can predict for a three-person household with an annual income of $40,000 that they're going to spend about $3,699 annually on their credit card. That's how much they're going to charge to their credit card annually. And I believe more independent variables will better help the model accurately predict how much a household is going to charge annually on their credit card. I believe two important independent variables that can be added to this is age and like the percent of the household that actually has a job, because that influences how much income is coming in. So the reason these extra independent variables will actually help is because, as seen before, when the independent variables were taken individually, the correlation wasn't very strong. When they're put together, it was much higher, going up to 0.8. So more independent variables will better help predict what this company was hired to do, which is to predict how much the household is going to charge on their credit card annually. All right, so thank you so much, and you have a great day.